Hello, I'm Matthew Corrin and I'm representing Group L in our presentation of a mechanical vibration project. The allocated project brief was one of a power belt transmission system. The other members of the Group L are shown here on the left-hand side and their relative roles. The vibrational behavior of an engine air conditioning ancillary belt is undertaken, modeled as an axially moving system. The system is studied without load, transmitted for simplicity. An axial tensile force is applied to the belt, and this represents the work done by the system. A point force is introduced into the midspan of the belt, and this helps us analyze the transient response. The dynamic behavior and the effect of axial speed is studied through a linear model of a simply supported beam in pin-pin configuration and with mass transport. This is shown in the schematic on the bottom left here in figure 2. A rubber V-belt was chosen from a manufacturer's catalogue, suitable for an air conditioning application. The belt data, density 1,034 kilograms per cubic meter, the Young's modulus of 30 gigapascals, and a moment of inertia of 8.14 millimeters to the 4. Cross-sectional profile of the belt is also shown here in figure 3, with a total cross-sectional area of around 18 millimeters squared. Test conditions include an axial tensile force, previously mentioned, of 100 newtons. The distance between the centers of the pulleys is 200 millimeters, which is also the distance between the supports of the beam. The point force magnitude used was 250 newtons. We then take a schematization of the infinitesimal beam element, and then using the force contributions, we can use this to develop our equation of motion. So one thing to note is we only consider transverse dynamics, which is the displacement field W with respect to x and t. We don't consider longitudinal dynamics of the system. So from that, we can develop the equation of motion, considering ρ is the beam density, A is the area of the beam element section, and Fa is the force amplitude of the point force. To completely define the problem, we introduce the boundary conditions, which are essentially the displacements and moments at 0 at both ends of the beam. The external force applied with the amplitude Fa is a single half period of a sine wave. Finally, we then develop the dimensionless form of the equation of motion, and this is useful to compare the relative contributions of each term. The continuous system is discretized using the Galerkin method, and then the displacement field is approximated on a basis of the Hilbert space. The sine function is chosen to implement the Galerkin method, as it respects the geometric boundary conditions, i.e. the displacements of the beam ends. The displacement field extension is taken to n terms. In our case, we used 8. The extension is substituted into the dimensionless equation of motion, and the result is projected on a basis of the Hilbert space. The compact matrix form of the discretized system is achieved, where Ft is the projected form of the forcing vector. From this, the state space form then provides 2n coupled equations, as shown in equation 8. The eigenvalue problem is then solved for different speeds, and the complex conjugate eigenvalues and eigenvectors are found. It is to note that the eigenvalues are all complex with 0 real parts. It can be seen that the natural frequencies are inversely proportional to the axial velocity, as shown in the table here. We increase the speed from 5 meters per second through to 90 meters per second, and especially the first term, omega 1 of natural frequencies, we see that drops quite substantially. This is shown more clearly on this graph here, where we have each natural frequency and its variation with axial speed. The first critical velocity, where the system becomes unstable, and the natural frequency becomes 0. This is found at 92.8 meters per second. All the natural frequencies decrease with increasing axial speed, as shown here. The eigenfunctions can then be approximated with the eigenvectors of the discrete problem using the expansion shown. It's to note that the real component of every mode begins positive and the imaginary component always begins negative, as shown here in these graphs. The blue line is the real component and the imaginary part is in orange with a dotted line. The dimensionless parameter Vf must be at least 0.2, otherwise numerical errors in the calculation of the eigenfunctions, like flipping of the real and imaginary parts, can appear in these plots. is to note these complex nodes are represented at 50 meters per second. On the following page, we see the same 8 complex modes, but represented at 90 meters per second. And one thing that we can notice from this is that the imaginary component of these complex modes is greater. This happens as we approach the first critical speed. Here are the eigenfunction contributions to the eigenvector contributions to the eigenfunctions at 50 meters per second. We see that most of the contribution comes from a single eigenvector. As we increase the speed, though, we see this contribution spread out more. So this is the same graph but plotted at 90 meters per second. And we see a greater spread of eigenvectors to build up the eigenfunctions. The complex nature of the eigenfunctions causes the mode shapes to change throughout a single period of vibration. This phenomenon is visible in figure 11 here, where the 8 modes are plotted for different instances of time during a half period of oscillation at 50 meters per second. As we increase the speed, we can see that the variation of shape of the eigenfunctions becomes more visible. So this is again, close to the first critical velocity. To find the transient response, we decouple the equation of motion with the modal coordinate transformation. The point force has an amplitude of 250 newtons, as mentioned before, and we have a period of 0.05 seconds. And it acts in the center of the beam in our initial studies. The period is chosen to ensure that the effects of the higher modes are still visible in the results. The modal coordinates of the space vector are evaluated and the transient response is obtained. The response is shown here for various locations along the belt when excited by the point force with the axial velocity of 50 meters per second. So that's in the graph in the bottom right there. Here we have a 3D plot of displacement, length and time of the transient response at the belt axial speed of 50 meters per second. If we increase the speed to 90 meters per second, we see that the period of oscillation increases. This is mainly due to the period of the first eigenfunction because this becomes much higher. And here we see the 3D plot of the response in time and space at 90 meters per second. Here's an animation showing the belt response at 50 meters per second when excited by the point force in the center of the belt. The colored circles are used to visualize the axial velocity of the belt. The point force here is applied at halfway along the beam. X over L is 0.5. Here we have the same simulation, but at 90 meters per second. And again, the colored circles represent the velocity of the belt. Here we have the response of the belt. X over L is 0.1, which is very close to the left-hand support of the belt. Here we have the superposition of the response at 0 and 50 meters per second. So note that the lower natural frequency of the first mode at higher speeds causes the response to lag behind the response of the system at 0 velocity. So if it's unclear, the red line is for the belt at 0 velocity, and then the black line is at 50 meters per second. Thank you for your attention, and I hope you enjoyed our presentation.